Welcome to the deep dive. Forget the headlines for a moment. Today we're looking at something really fundamental, something you probably interact with multiple times a day, the chemistry happening right in your kitchen.
Yeah, definitely. We've been digging into Simon Quellen Field's book, Culinary Reactions, the everyday chemistry of cooking.
And it's fascinating stuff. It covers everything from, acids and bases to foams and emulsions.
Exactly. What's great is how it explains the science behind why things work in cooking, or sometimes why they don't work.
Right. Those aha moments. Our mission, as always, is to pull out those key insights for you.
So let's jump in. We're starting with something that seems super basic, but actually has some hidden complexity, measuring ingredients.
Okay, measuring and weighing. Seems simple enough.
Well, yes and no. The book makes a good point that for general cooking, a little variation here or there, often totally fine.
Okay.
But baking, that's a different story. When a recipe says a cup of flour, it sounds precise, but flour's density can vary quite a bit.
Density. Right. So how you pack the cup matters.
Huge difference. If you just scoop it loosely, you get less flour by weight than if you pack it down firmly.
Even though it looks like the same amount?
Exactly. And that difference in mass, especially in baking, where ratios are so critical, well, it can really impact things. Gluten development, final texture.
So a packed cup versus a scooped cup could mean a dense cake instead of a light one.
It absolutely could. It's about what's actually in that space, not just the volume.
That makes sense. What about calories? People track those. The book touched on estimating at home.
Yeah, it did. It pointed out that, home calorie counting isn't going to be perfectly exact. There's just too much variability.
Sure, ingredients differ, portion sizes.
Right. But understanding the relative calorie density is still pretty useful. Like, the book mentions 28 grams of beef jerky is about 116 calories.
Okay.
And the same amount of pork sausage. Around 95 calories. It's not about obsessing, but it gives you a better picture.
Good context. Okay, moving on to something maybe a bit more dramatic. Foams, whipped cream, meringue. What holds them together?
Foams. Okay, so basically a foam is just gas bubbles trapped in a liquid or a solid.
But what stops them from just popping?
Proteins. That's usually the key.
Yeah.
Proteins are made of amino acids, and they act like a support structure. They form a sort of film around each air bubble.
How do they do that?
Well, proteins have different parts. Some parts love water hydrophilic, and others hate water hydrophobic.
Okay.
So in something watery like egg whites, the water-loving bits stick to the water, and the water-hating bits try to get away. They end up at the surface, the air-water interface.
So they naturally line up right where the air bubble meets the liquid.
Exactly, creating this stabilizing network.
And egg whites are particularly good at this, the book says. Why is that?
Egg white proteins are kind of special. When you beat them, they denature, unfold, and then bond together really effectively.
Oh.
A big part of it is sulfur atoms in the proteins. They form these things called disulfide bridges.
Like tiny chemical links?
Yeah, exactly. Like little rivets holding the coating network around the bubbles firmly together. Makes the foam much more stable.
Sulfur, saving our soufflés. Okay, what about sugar foams, like marshmallows? That feels different.
It is quite different. Sugar foams rely on the properties of sugar itself at high temperatures. You heat sugar syrup way up to about 300 Fahrenheit, 150 Celsius.
The hard crack stage.
That's the one. The syrup gets incredibly thick, viscous. Then, as it cools, it hardens into this glassy structure that traps the air bubbles. The hard sugar is the structure.
And whipped cream, where does that fit in?
Whipped cream is another foam, but stability there comes mainly from the fat globules.
From the fat.
Yep. When you whip cream, you're forcing air in and bashing the fat globules around. They partially break and then clump together, forming a network that traps the air. There are proteins involved too, coating the fat globules, which helps stabilize things as well. But the fat network is key. Different methods, same foamy result, basically.
Cool. Okay, let's switch gears. Emulsions. The classic oil and water problem.
Yes. The eternal kitchen struggle. You whisk up a vinaigrette, turn your back, and separation.
So what is an emulsion technically, and how do we get oil and water to actually cooperate?
Well, an emulsion is just a stable mixture of two liquids that normally refuse to mix, like oil and water. Milk, cream, mayonnaise, all common emulsions.
And why don't they mix naturally?
It comes down to molecular attraction. Water molecules are really attracted to each other through hydrogen bonds. Very strong attraction.
Okay.
Oil molecules, not so much attraction to water. So the water molecules stick together tightly and essentially push the oil molecules out, causing them to form separate layers.
Like cliques at a party.
Exactly. So to get them to mingle, you need a go-between, an emulsifying agent.
A molecular diplomat.
Kind of.
Yeah.
These molecules have two sides, one that likes water, hydrophilic, and one that likes oil, lipophilic.
So it can hang out with both groups.
Right. It positions itself right at the boundary, the interface, between the tiny oil droplets and the water, reducing the tension and letting them stay mixed together.
What are some common ones we use?
Egg yolks are famous for. Lecithin is the key phospholipid there. Soybeans also have lecithin. Milk proteins are also great emulsifiers.
And things like xanthan gum. I see that in dressing sometimes. Is that an emulsifier too?
Not exactly. It's more of a stabilizer. Emulsifiers create the emulsion, but stabilizers help maintain it over time.
Ow.
They usually work by thickening the water phase, makes it harder for the oil droplets to move around, bump into each other, and merge back together. Xanthan gum, gum arabic, they add viscosity.
Got it. Emulsifiers create, stabilizers maintain. Okay, next up, colloids, gels, and suspensions. These sound a bit science labby.
They do sound technical, but you deal with them all the time. A colloid is basically just tiny insoluble particles spread evenly throughout another substance, like milk fat globules dispersed in water, or even fog water droplets in air, or smoke solid particles in air. The particles are too small to see individually easily, but they're suspended.
Okay. And gels, like Jell-O.
Gel is the perfect example. A gel is a type of colloid, specifically a liquid-based one, where the dispersed particles link up to form a kind of network.
The 3D structure.
Exactly. A network that traps the liquid, usually water, within it, giving you that semi-solid, wiggly texture. Pectin in jam does this. Gelatin does this. Cooked egg white proteins do this.
Like a microscopic sponge holding water.
That's a great way to think about it.
And starch. We use it to thicken sauces, but the book says it forms gels too.
It does. Starches are polysaccharides, long chains of sugar molecules. When you heat starch granules in water, they swell up, absorb water, and the starch molecules amylose and amylopectin start to leak out and tangle up.
Creating that network.
Right. That tangled network traps the water, thickening the liquid, and if the concentration is right, it forms a gel as it cools. Think cornstarch pudding.
Makes sense. The book also mentioned agar and agarose. From seaweed?
Yeah, those are other gelling agents. They're interesting because they can form quite firm gels, even at low concentrations. And they set at higher temperatures than gelatin, which is useful sometimes.
And protein gels, again, we mentioned egg whites. Any others?
Oh, sure. Heating meat denatures its proteins, causing them to link up and form a gel network that holds onto water. That's why cooked meat firms up. Custard set because the egg proteins form a gel.
So many gels. Okay, let's talk fats and oils.
Yeah.
Flavor, texture, critical stuff.
Absolutely. The lipids, we know they don't mix with water, high in calories.
Right.
But chemically, there's more going on.
Like the difference between a solid fat and a liquid oil.
Right. Temperature is key, but fundamentally they are mostly triglycerides. That means a glycerol molecule backbone with 3 fatty acid molecules attached.
And the different types, saturated, monounsaturated, polyunsaturated.
That difference is all in the fatty acid chains. Saturated fats have only single bonds between carbons. The chains are straight.
So they pack together easily.
Exactly. Like stacking planks of wood. That close packing makes them solid at room temperature. Think butter or lard.
Okay. And unsaturated.
Unsaturated fats have double bonds between some carbons. Monounsaturated has 1 double bond. Polyunsaturated has 2 or more.
And double bonds make a difference, how?
Each double bond creates a kink, a bend in the chain.
Ah, so they can't pack as tightly?
Precisely. Those kinks keep the molecules further apart, lowering the melting point. That's why oils like olive oil or vegetable oil, rich in unsaturated fats, are liquid at room temp.
What about omega-3s and omega-6s? We hear those terms a lot.
Those are types of polyunsaturated fatty acids that are essential for us. Our bodies can't make them. The number just tells you where the first double bond is located along the chain. That position affects how they function in our bodies, like in making hormones.
And trans fats, they get a lot of negative press.
Rightly so. Trans fats are mostly created artificially when liquid oils are partially hydrogenated. Hydrogen is added to make them more solid, like in shortening or some margarines.
What's the problem?
The process can change the shape of the remaining double bonds into a trans configuration, which is straighter than the natural cis form. Our bodies don't handle these well, and they've been strongly linked to increased risk of heart disease. That's why they're being phased out.
So, tiny changes in shape, big health consequences. Okay, moving from fats to something almost sparkly. Crystallization.
Yeah. It sounds pretty and it is important. Crystallization is just molecules arranging themselves into a very ordered, solid structure, super relevant for sugar and fat and cooking.
Like making candy. You want smoothness, not grittiness.
Exactly. Grainy candy means large, unwanted sugar crystals formed. Controlling crystallization is key. You want lots of tiny crystals, or sometimes no crystals at all.
How do you control it?
Things like adding interfering agents like corn syrup or an acid like cream of tartar can disrupt the sugar molecules from lining up too easily into large crystals. Careful temperature control is also vital.
And chocolate tempering. That sounds like a high-stakes crystallization process.
It really is. Cocoa butter, the fat in chocolate, can crystallize in several different forms, called polymorphs. Only one specific form, the beta crystal, gives you that glossy shine, hard snap, and smooth melt.
So tempering is about forcing it into that one specific crystal form.
You got it. It involves carefully heating and cooling the chocolate with agitation to encourage only those desirable beta crystals to form and discouraging the others, which can cause issues like fat bloom, that chalky white coating.
Tricky stuff. Okay, let's circle back to proteins. We know they do foams and gels. What else are these kitchen workhorses up to?
Oh, proteins are involved everywhere. Remember, they're long chains of amino acids folded into specific 3D shapes. That shape dictates what they do.
And denaturation is when they lose that shape.
Exactly.
Oh.
Heat, acid, physical force like beating these things can cause the protein to unfold, to denature.
And what happens then?
Once unfolded, the proteins can interact with each other in new ways. Often they clump together or coagulate. That's what happens when egg white cooks. The denatured proteins link up and form a solid network.
The book mentioned ovalbumin in egg whites.
Yeah, that's the main protein in egg white. It denatures relatively easily with heat, making eggs great binders and thickeners.
And milk proteins. Cheese making involves them coagulating too, right?
Right. But milk proteins, mainly caseins, behave a bit differently. They tend to clump together when the pH drops, when it gets acidic, or when you add an enzyme called rennet.
Which is how you get curds for cheese.
That's the process. Acid, or rennet, makes the casein proteins aggregate, separating from the whey, forming the curd. So yeah, proteins are busy building structures all over the kitchen.
It's amazing. Now, let's zoom out a bit to biology. Microorganisms. Our kitchens are full of them, good and bad.
Absolutely not sterile labs. And that's often a good thing. We rely on beneficial microbes like yeast for bread, bacteria for yogurt and cheese. Of course, we also want to avoid the ones that cause spoilage or illness.
Let's start with yeast, the bread maker. How does that work?
Yeast is a fungus, single-celled one. Its main trick in baking is fermentation. It eats the sugars in the dough.
And produces?
Carbon dioxide gas and alcohol. The CO2 gets trapped in the dough's gluten network, creating bubbles and making the bread rise. Different yeast strains can also add different subtle flavors.
And sourdough uses wild yeast.
Wild yeasts and bacteria living together in that starter culture. It's a whole ecosystem. The bacteria produce lactic acid and acetic acid, which gives sourdough its characteristic tangy flavor and chewy texture. It's a more complex fermentation.
Very cool. What about yogurt? Also fermentation.
Yep. Specific bacteria, like lactobacillus species, are added to milk. They ferment the milk sugar, lactose, into lactic acid.
And the acid thickens the milk.
Right. The acid lowers the pH, causing the milk proteins, those caseins again, to denature and form a gel-like network. That's your yogurt texture, plus the tangy flavor from the acid.
And cheese. Similar idea, but more complex.
Kind of. You start by coagulating the milk proteins, usually with rennet or acid, to form curds. But then, for many cheeses, specific bacteria or even molds are added or encouraged to grow during the aging process.
And they create the final flavor and texture.
Exactly. Their metabolism produces all sorts of compounds that give different cheeses, cheddar, brie, blue cheese, their unique characteristics. It's microbial magic.
And food preservation often works by stopping these microbes, right? Salting, drying.
Exactly. Those ancient techniques work by making the environment hostile to spoilage microbes. Salt draws out water through osmosis. Drying removes water altogether. Fermentation itself can be a preservation method because the acid produced inhibits other, less desirable microbes.
Understanding the bugs helps us control them. Okay, let's talk acids and bases, fundamental chemistry.
Absolutely. Sour versus slippery. Acids donate hydrogen ions, H+, taste sour. Bases accept hydrogen ions, often feel slippery.
And the pH scale measures this. Low pH is acidic, high is basic.
Right. 0 to 14, 7 is neutral. Lemon juice is down around pH 2, vinegar maybe 3. Baking soda dissolved in water is basic, around 8. Drain cleaner is way up there, like 14.
Big range. How do acids affect cooking?
Big time, especially with proteins. We saw acid coagulating milk for yogurt and cheese. Acid in marinades helps tenderize meat by breaking down some connective tissue proteins. Ceviche uses acid to cook fish by denaturing its proteins.
And bases, are they used much?
Less often directly, but yeah. Nixtamalization is a key one, soaking corn in an alkaline solution, traditionally lime water.
What does that do?
It softens the corn, makes nutrients like niacin more available, changes the flavor, and allows it to form dough for tortillas. Really important process.
Wow. And the book mentioned foods changing color with pH.
Yeah, some natural pigments act like built-in pH indicators. Anthocyanins, the pigments in red cabbage, are a classic example.
They change color depending on acidity.
Exactly.
Yeah.
Red cabbage juice turns reddish in acid, purplish when neutral, and greenish blue, or even yellow in strong base. You can do fun experiments with it. Chameleon eggs, the book called them.
Fun. Okay, 2 more reaction types. Oxidation and reduction. Sounds very chem lab.
It does, but it happens constantly in the kitchen. Oxidation is losing electrons. Reduction is gaining them. Think about cut fruit browning.
Apples, avocados, or they turn brown so fast, that's oxidation.
It is. Specifically, it's an enzyme called polyphenol oxidase doing the work. When you cut the fruit, the enzyme gets exposed to oxygen from the air.
And it reacts.
It reacts with phenolic compounds in the fruit, turning them into brown pigments called melanins. It's actually a defense reaction for the plant.
So how do we stop our guacamole going brown? Lemon juice.
Lemon or lime juice works great. The acid lowers the pH and inhibits that enzyme. Reducing oxygen exposure also helps pressing plastic wrap right onto the surface. Blanting works too, by denaturing the enzyme with heat.
Okay. What about fats going rancid? Is that oxidation too?
It is. Fats and oils can oxidize, especially unsaturated ones. It's often a chain reaction started by free radicals.
Then that causes
breakdown of the fat molecules into smaller compounds that smell and taste bad, that rancid flavor. Antioxidants, naturally present or added, can stop this chain reaction.
Good to know. Okay, we've covered reactions. What about practicalities like scaling recipes? Making more or less? Not always straightforward, is it?
Definitely not just simple multiplication or division. A key thing the book highlights is the surface area to volume ratio.
How does that affect things?
Well, when you make something bigger, its volume increases faster than its surface area. Think about cooking times.
Right. A giant cake takes way longer to cook through than cupcakes.
Exactly. Heat has further to travel to get to the center of a larger item. So doubling ingredients doesn't mean doubling cooking time. It's usually much more. The reverse is true too. Smaller things cook faster.
And drying.
Same principle. Drying happens at the surface. More surface area relative to volume means faster drying. Think thin jerky versus a thick piece of meat.
And gravity. Does that matter more with bigger batches?
It can, yeah.
Yeah.
Especially for things that rely on delicate structures like foams or really light cakes. The sheer weight in a very large batch might cause collapse before it's fully set or baked. You might need to adjust structural ingredients, not just scale everything linearly.
So scaling needs some thought about the physics too. Okay, on to the big one. Heating. This changes everything.
Fundamentally, heating drives so many crucial reactions. Let's start with browning. 2 main types, caramelization and the Maillard reaction.
Caramelization is just sugars, right?
Heating sugars directly to high temperatures breaks them down and reforms them into hundreds of new compounds, giving you that characteristic brown color and complex, nutty, slightly bitter flavor of caramel.
And Maillard, that's the one chefs rave about.
It's the holy grail of flavor for many things. Maillard reactions happen between amino acids from proteins and reducing sugars when heated.
So not just sugar, but sugar and protein.
Yeah, exactly. And it's responsible for the browning and incredible flavor of seared steak, baked bread crust, roasted coffee, fried onions. So many delicious things. It creates literally hundreds of different aroma and flavor molecules.
Wow, so that's where that deep cooked flavor comes from. What else does heat do chemically?
Well, we've talked about protein denaturation. Heat makes proteins unfold and coagulate, changing texture. Think meat firming up, egg setting.
It also dries things out.
Yep, dries off water, concentrating flavors, but also potentially making things dry if overdone. Heat creates new flavors, can change nutritional value, sometimes for the better, sometimes degrading sensitive vitamins.
And the book warned about very high heat potentially creating carcinogens.
Yeah, a brief mention. Things like heterocyclic amines in heavily charred meat, or acrylamide in very brown, starchy foods like overcooked fries or burned toast. Generally, avoiding excessive charring is a good idea.
Got it. And heat activates leavening agents.
It often does. Baking powder, for instance, usually has components that react and release carbon dioxide gas, mainly when heated in the moist batter. Baking soda needs acid, but heat speeds up the reaction. That gas production is what gives cakes and breads their rise.
Heat is truly the engine of transformation in cooking. Okay, last section. Boiling, freezing, and pressure. Manipulating states of matter.
Exactly. Boiling happens when a liquid's vapor pressure equals the surrounding atmospheric pressure. For water, that's 100 degrees C or 212 degrees V at sea level.
Does adding salt make water boil faster? I hear that all the time.
It actually makes the boiling point slightly higher. The effect on boiling time is pretty negligible for the amount of salt you'd add to pasta water. The main point of salting the water is to season the food.
Okay, myth busted. But altitude does affect boiling point.
Big time. Lower atmospheric pressure at high altitudes means water boils at a lower temperature.
So food takes longer to cook.
Yes, because the water isn't as hot. You often need to adjust cooking times or use a pressure cooker.
And freezing. We know it preserves food, but it changes texture sometimes.
That's down to ice crystals forming. Water expands when it freezes, and those sharp crystals can puncture cell walls in fruits and vegetables.
Making them mushy when thawed.
Often, yeah. Faster freezing creates smaller ice crystals, which causes less damage. That's why commercial frozen foods often have better texture. And remember, salt and sugar lower the freezing point of water.
Which is useful for making ice cream. The salt makes the ice bath colder.
Exactly. The salt dissolves in the melting ice, lowering its freezing point well below 0 degrees C or 32 degrees Fahrenheit. This super cold brine freezes the ice cream mixture quickly while it's churned, leading to smaller ice crystals and a smoother texture.
Clever. And pressure cookers speed things up.
They work by increasing the pressure inside the pot. Under higher pressure, water boils at a much higher temperature, maybe 120 degrees C or 250 degrees Fahrenheit.
So the food cooks in hotter water.
Precisely. That significantly higher temperature dramatically speeds up cooking, especially for tough cuts of meat or dried beans that usually take ages.
Amazing how we manipulate these basic physical principles. Wow, okay, that was a real journey through kitchen chemistry.
It really was. From weighing flour to the Maillard reaction, it's clear chemistry is happening constantly, shaping everything we taste and touch in our food.
Yeah, understanding even a little bit of the why behind cooking techniques really changes how you see things. It's not just following steps, it's managing reactions.
Absolutely. It gives you a much deeper appreciation for both the science involved and the culinary artistry that chefs and home cooks use every day.
So next time you're whisking an egg white or searing a steak, maybe think about those proteins unfolding or those sugars reacting. It's pretty incredible stuff.
It really is. And here's something to chew on. Think about how cooks, for centuries, figured out how to make cheese or bake bread or temper chocolate through trial and error, essentially mastering complex chemistry long before scientists could explain exactly what was happening at a molecular level. That intuitive understanding, combined with a bit of modern science, really elevates the craft.
A perfect final thought. Thanks for exploring the depths with us.